This is Professor Ann Spihar, Assistant Professor of Economics from the University of Alaska Southeast. This is a lecture in Ecological Economics, Chapter 6 from the textbook Ecological Economics Principles and Applications by Herman Daly and Joshua Farley. This is Part 2, where we will discuss renewable biotic resources. In Part 3, we will discuss ecosystem services and waste absorption capacity. In this lecture of Part 2, we will focus on three basic categories of biotic resources. First are renewable resources, the elements of ecosystem structure that provide the raw materials for economic processes. Second are ecosystem services, defined as the ecosystem functions that are of value to humans and generated as emergent phenomena by interacting elements of the ecosystem structure. And finally, waste absorption capacity, an ecosystem service that is sufficiently distinct from the others to warrant a separate treatment. We will discuss each here in Part 2, beginning with renewable resources. We will treat biological resources as material stock flow resources, that is, as elements of ecosystem structure. Biological stocks are capable of reproduction and are therefore considered renewable. Renewable resources are elements of the ecosystem structure that provide raw materials required for economic processes. For example, fish and timber, soil and air and water. These renewable biological or biotic resources are treated as stock and flow resources. Unlike non-renewable resources, biological stocks can be renewed through reproduction. And this means that we can extract these resources in a sustainable fashion that will allow the given stock to regenerate. And this can be represented by a graph. Let's set up a graph in XY space and have on the x-axis the stock, or population, or amount of the resource at a given time. On the y-axis, we can represent the flow variable. The flow variable will represent reproduction, a rate of reproduction. So for a given x value, the y value will tell us how many young were produced, given the stock amount of x. At every point on the x-axis, the increase of stock from the reproduction of that given amount of x will be added to the next x stock amount on the x-axis, like this, as represented from the following video from the Conservation Strategy Fund's collection of environmental economic lessons. This entire video has been provided on the Blackboard course website, and it is required that students listen to this recording following Part 2.
Population was here, then the fish is growing by this amount. So we know we can take that amount, and by next time the population wouldn't have changed. If the population was still here but we took below that line, then next period the population would be greater. If we keep taking that amount, the population will grow and grow and grow until it reaches here. Now we're at the growth line for this fish. If we take this much again, the population isn't going to change. If the population were here but we took this much fish, then we're taking more than that period's amount of growth, and next time the fish population will be lower. If we still take that much the next period, then it will be lower and lower.
So let's consider the 45-degree line. This line represents the entire amount of new growth or possible new growth that could be extracted each year from some population. Now the 45-degree line is the maximum rate of extraction possible that will leave the base amount. If we want to preserve the stock, we must be sure that we extract on or below this 45-degree line. If no extraction occurs, we could also draw a line that would tell us how the stock grows each year. This is the growth or sustainable yield curve that you see here. This new curve would inform us of the sustainable yield. Since there is an average rate of population increase, this increase represents the sustainable harvest that can be removed without affecting the base population. Sustainable yield, then, is the net annual reproduction from a given stock. There are many uncertainties in knowing what this reproduction rate actually is. Many things affect this: rainfall, temperature, growth of predation, disease, etc. We have to be very careful on estimating this, as a mistake in extraction rates could result in population collapse. Also, populations do not grow forever. We learned this in the reintroduction of wolves in Yellowstone. They grew very rapidly at first and then began to collapse as the elk were decimated, then grew again and then began to stabilize. The point at which they stabilized around an equilibrium is called the carrying capacity and is represented on this graph by capital K. This is the population that can be sustained by a given ecosystem. The maximum sustainable yield is represented by capital MSY and represents the maximum harvest that can be extracted without impacting stock depletion. This particular graph suggests that we have about a 30% growth rate at the MSY maximum sustainable yield. This is because the value MSY is about 1/3 of the way to the 45-degree line. This is actually a very large number. In reality, it is much more like about a 1% per year and even less for many species that carry significant economic importance. Again, the y-axis shows us the increase in stock for each period and measures for us the estimate of growth or harvest that flows into the next period. But note that it can go either way. It can increase the stock the next period or it can decrease it depending on how much is harvested. If our estimates are accurate and the sustainable yield curve accurately represents the increase in stock for each period, and this is a very big if, and mistakes have been made, but if it is accurate, then this curve represents the possible harvest allowed for each year without impacting base populations. Notice the arrows in the graph. Well, these arrows represent the direction of population growth, or in other words, the impact on base populations. The base population can grow, represented by an arrow pointing to the right, or populations cannot grow, in which case the arrows point to the left. Note that the arrows to the left are above the sustainable yield curve and arrows pointing to the right are below it. Again, right on the curve keeps the base population stock just as it is. For example, a harvest at R will reduce the stock to S double prime, and a harvest at S prime will allow the stock to increase to R double prime. Notice the point labeled CD. This is called the critical depensation level. This is the point at which the stock is unable to sustain itself even without any harvest and begins to collapse. We really do not want to go anywhere near this point. So if we are estimating, we will need a very big confidence interval around this point. We call this point on the x-axis of critical depensation the minimum viable population. Any stock amount below this point is likely to lead to a collapse in the population. Note that there are points where the sustainable yield curve enters into negative values that is below the CD point. A negative harvest is required at this point, and this means that new populations must be added to ensure that the existing stock is maintained. In most cases, ecologists do not know exactly where that CD point lies, and this is often contentious among those engaged in harvesting for profit or recreation. We will use this understanding in Chapter 12 when we examine the microeconomics of biotic resource allocation. So now let's suppose we harvest right at the point of carrying capacity, at point capital K. Let's say we harvest capital Q amount. The amount from K to Q would reduce the population to point R double prime. But the population would continue to grow at stock amount R double prime. Resources per individual, for example, in the population might increase, leading to increased fertility and growth rates. But if we continued and at R double prime, capital R was extracted, then we would be at S double prime the next period. The idea is to stay as close as possible to the sustainable yield values on the sustainable yield curve. This curve can be used for most renewable resources, including lumber or forests, fish catch, or any biological resource that is replenished by reproduction. So, in summary, sustainable yield curve provides us with some critical concepts. First of all, we have sustainable yield as being identified as the net annual reproduction from a given stock. Critical depensation point is the minimum viable population and represented by CD. Carrying capacity is the equilibrium around which a population has stabilized, and that's represented by capital K. And this is a very useful pedagogical device. It provides us with an idea of maximum sustainable yield and concepts of harvest in proportion to a given resource stock. Unfortunately, there are drawbacks to it. There is a high degree of uncertainty. For example, the population, even reproductive rates, are hard to identify, and there are many external factors that impact reproduction rates as well as the population. And finally, it is a dynamic process, and it isn't always very useful for using this tool in setting quotas. We will talk a lot more about this in Chapter 12. Well, this concludes Part 2. In Part 3, we will discuss ecosystem services and waste absorption capacity. This is Professor Anne Orion Spihar from the University of Alaska Southeast.